So to continue with solving equations using substitutions, let's try first to solve a homogeneous equation that is written on the screen. So how do we know that this is a homogeneous equation? Again, remember last time I suggested that what you can do is so to check if this thing is homogeneous, you need to substitute y equal to vx. So if you do that, you'll have x squared plus vx squared dx plus x squared minus xy, minus x times vx dy equal to 0. And then we can see that in all of these terms, if I distribute square v square x square dx plus x square minus v times x square dy equal to 0, in all of these terms, I see a factor of x squared. So I can pull it out to have x squared times 1 plus v squared dx plus 1 minus v dy, and this is equal to 0. Okay, so x squared is a multiplier on the left, so I can just divide everything by x squared. So in one, let's divide everything by x squared. What is left is 1 plus v squared dx plus 1 minus v dy equals 0. So what you see is that there is no x left in this expression. And if there is no x left, then that means that the equation is homogeneous. All right, so if it is homogeneous, then what we do is we finish substitution. And to finish substitution, we need to replace derivative of y with respect to x by the derivative of v with respect to x. So we already have seen that if y is vx, then by the product rule, y prime is v prime x plus vx prime, and x prime is 1, so v prime x is v. Since my equation is written in this form, in a differential form with dx and dy, we have to rephrase then the statement in terms of differentials. So dy over dx, right, that's what y prime is. That is dv dx, v prime, times x plus v. And then we are going to multiply both sides of this by dx. And so we get that dy should be equal to x times dv, because this dx will cancel with this dx, plus v times dx. And so now if I sub this into the equation, I will have 1 plus v squared times dx plus 1 minus v times dy is x dv plus v dx, and the whole thing is equal to 0, right? So I took this equation that we already established and I replaced dy by this. All right, so we have that. So what does this give me? It gives me 1 plus v squared dx plus x times 1 minus v dv, if I distribute 1 minus v, plus v times 1 minus v dx, and the whole thing is equal to 0. And so now if I combine everything with dx together, I'll have 1 plus v squared. Now if I distribute v here, I'm going to get v minus v squared. So plus v minus v squared times dx plus x times 1 minus v dv, and this should be equal to 0. All right, and so now we can simplify the first parenthesis, v squared minus v squared, so 1 plus v dx plus x times 1 minus v dv, this is 0. And we said that if I use a substitution y equal to vx on a homogeneous equation, I'm always going to end up with a separable equation. And indeed, in this case, if I separate the sides, so 1 plus v dx is equal to minus x 1 minus v dv. Move x's on one side and v is on the other side. By the way, 1 minus v is actually, if I distribute minus, is x times v minus 1. So dividing by x and dividing by 1 plus v, I have dx over x is equal to v minus 1 over v plus 1. 1 plus v plus 1 is the same thing, times dv. And so now I can integrate. So then the integral of dx over x is equal to integral of v minus 1 over v plus 1 dv. Integral of dx over x, of course, is natural log of absolute value of x plus c. And I need to figure out how to compute the integral of v minus 1 over v plus 1. And there I'm going to use a substitution, u equal to the denominator, u equal to v plus 1. So then du is dv. And the integral becomes, so on the bottom I have u. dv and du is the same thing, so du. And what is v minus 1? V minus 1 I can write as v plus 1 minus 2, and v plus 1 is u, so this is u minus 2. So u minus 2 goes on the top. I don't need this scratch work. And so what's left now, if I divide by u, integral of 1 minus 2 over u du, which is integral of 1 times du minus 2 integral of 1 over u du, and first integral is u, and the second integral is ln of absolute value of u. And so what we got is that u minus 2 ln absolute value of u is ln absolute value of x plus c. Okay, now we remember what u was. U is v plus 1, right? That's a substitution that I made here. So I need to replace all u's by v plus 1. So v plus 1 minus 2 natural log absolute value of v plus 1 equal to ln absolute value of x plus c. And then we remember also that we're actually looking for y as a solution and not v. Y and v are related by y equal to vx. So v is y divided by x. So now the last step, I'm going to replace all v's by y over x to get y over x plus 1 minus 2 natural log absolute value y over x plus 1 equal to ln absolute value of x plus a constant. And that is a general solution of my equation, right? Again, first order equation. General solution will have one unknown constant. All right, next example. I want to solve an equation like this. We see that this equation looks more or less like a linear equation because xy prime plus y looks like a left-hand side of a linear equation. But the problem is that on the right side I have y squared. So the equation is nonlinear, but it has a form that we described last time as a Bernoulli's equation. So Bernoulli's equation. And this equation can always be solved by using substitution v equal to y to the power 1 minus n, where n is the power of y here. So use substitution. V equal to y to the power 1 minus 2. So v is 1 over y. Saying that is the same thing as saying y is 1 over v, or v to the negative 1. And if y is v to the negative 1, then y prime is going to be minus v to the minus 2 times v prime. So now I'm ready to substitute. I have x times y prime minus v to the minus 2 v prime plus y, which is v to the negative 1, equal to x squared times y squared. Y is v to the negative 1 squared. So this is x minus x v to the negative 2 v prime plus v to the negative 1 equal to x squared, and v to the minus 1 and then squared is the same thing as v to the minus 2. And so now we multiply by v squared both sides. And when you do that, v to the minus 2 will go away, and v squared times v minus 1 to the power minus 1 is just v. So what's left is minus x v prime plus v equal to x squared, and that is a linear equation. And if it's a linear equation, then we can use integrating factor. But actually, before we use integrating factor, we need to write the equation in the standard form. So I divide everything by minus x to get v prime minus 1 over x v equal to minus x, because x squared over x is x, and x squared over minus x is minus x. So the integrating factor is going to be mu of x equal to e to the power integral of minus 1 over x dx. Let me again assume here that x is positive. Because if x is positive, things are going to look simpler. So this is e to the power minus integral of 1 over x ln absolute value of x. When we compute the integrating factor, we're not adding an arbitrary constant. Then if x is positive, like I assumed, then I can drop the absolute value sign. Then if there is a constant in front of ln, I can always bring it inside the log and it becomes a power. So this is e to the ln x to the minus 1. And e and ln cancel each other out, so what you get is x to the minus 1. And then I know that if I multiply my equation here by the integrating factor, then the left-hand side will look like integrating factor 1 over x times v quantity prime, right? The entire left-hand side by the integrating factor is going to be the integrating factor times v prime equal to minus x, right-hand side, times the integrating factor x to the minus 1, which is 1 over x. So x goes away, and you have all of this equal to minus 1. So then integrating both sides, integral of a derivative is a regional function. And this should be equal to the integral of what I have on the right, integral of minus 1 dx, which of course is minus x plus c. And I can solve now for v by multiplying both sides by x. So v is minus x squared plus cx. And then I recall that I'm actually solving the equation in terms of y, so I have to relate y and v. What is y? Y is v to the minus 1, or v is 1 over y. So if v is like we have found here, then y, which is equal to 1 over v, is going to be 1 over cx minus x squared. And so then our Bernoulli's equation now is solved. Okay, in this next example, I want to solve an equation like this. And you can check that this equation does not actually conform to any of the types that we have discussed so far. It's not a linear equation, clearly, because it has y squared in it. It's not a separable equation because the right-hand side is not a product of a function of y and a function of x. It's not going to be an exact equation. You can verify that as well. It's not a homogeneous equation because if I replace y by vx, so actually let's try to verify that. If y is equal to vx, then on the right side I'm going to have vx plus x squared, which is x squared times 1 plus v quantity squared. So that will give us y prime is equal to x squared 1 plus v squared plus v. And certainly x does not cancel out. If x doesn't cancel out, then this is not a homogeneous equation. So let's get rid of that, and maybe actually let's check, maybe it is Bernoulli's equation. So y prime, I'm going to expand the right hand side, so y prime is y squared plus 2xy plus x squared plus 3. I can move 2xy on the right side. Y squared minus 2xy is now y squared plus x squared plus 3. So then this part, the left hand side equal to y squared, looks like Bernoulli's equation, but then you're adding something else. So at the end, this is not Bernoulli's because it's in a different form. So at this point, we have two choices: either we give up and go home, or we devise a new way of solving an equation like this. And the natural thing to do here actually is, because the right hand side is a function of y plus x, then, as I have written here, the natural choice is to try a substitution v equal to y plus x. And if I make that substitution, then I can solve y for v. And so I'm going to get this. And I can take the derivative of both sides. So y prime will be v minus 1. We sub this in. The left-hand side is v prime minus 1. Right side is v squared plus 3. Solve this for v prime. And this is a separable equation, so we should be able to solve it. All right, so dv dx, then v prime is dv dx. Separate variables. We get an equation like that. Then integrate both sides and hope that you will be able to compute the integrals. So let's see, the integral on the right, of course, is very simple. It's a log of absolute value of x. What about the integral on the left? So then integral dv over v squared plus 4. This actually is an integral of dv over v squared plus 2 squared. And that is a table integral. So if you go to the table, you see that this is an arctangent of v divided by 2 itself multiplied by 1/2. So it's 1 over a times arctangent of v over a, but in this case, a is 2. All right. And so then 1/2 arctangent of v over 2 is an integral of dx, which is x plus a constant. Well, in this case, actually, we can solve this equation for v, right? Because if I have half of arctangent of something is x plus c, that means that arctangent of v over 2 is 2x plus 2c. Now notice a trick that I'm going to use. C is a generic constant, so 2c is a generic constant. So the generic constant simply can absorb 2, and we can keep writing just c. Okay, so then if arctangent of something is equal to something else, then the something, in this case v over 2, is tangent of the right-hand side, 2x plus c. And then solving for v will be 2 tangents of 2x plus c. And now remember that we're actually solving an equation for y, so we have to be able to determine y from v. Y and v are related in this way. Y is v minus x. And so y is v minus x and v is y minus x. So y minus x is 2 tangents of 2x plus c. So I can solve for y completely. Y is x plus 2 tangents 2x plus c. Okay, and so then we're trying to solve our initial value problem. So let's see. So to solve the initial value problem, I need to plug in 0 for x and 1 for y. So we get, so we solve the IVP. Y is equal to 1, x is equal to 0, plus 2 tangent of what? 2 times 0 plus c. So this gives us, so 2 times 0 is gone. This 0 is irrelevant. So we have that 2 tangent of c is equal to 1. So tangent of c is 1/2, and therefore c is arctangent of 1/2, whatever this is. And so finally, we can compute what y is by plugging in what c is into the expression, right into our one parameter family. So y is x plus 2 tangents 2x plus arctangent of 1/2. And that's a final solution. So as usual, you can see in all of these examples, the most difficult part probably is integration, and then the actual solution technique of the ODE is not really that challenging. All right, so next time we're going to talk about applications of first order ODEs.